Bismillah ar-Rahman ar-Rahim. Today we will discuss measurement of hydrogen and CO2 level. Hydrogen ion concentration and pH. pH is a measure of the hydrogen ion activity. This is much reasonable, or concentration in liquid. It is defined as the negative logarithm to the base 10 of hydrogen ion concentration. In other words, pH of 7.4, which is the normal value in the human beings, equal 40 nanomole per liter of hydrogen ion concentration. Or if we want to shift it to the negative logarithm, the power of 10, as we said before, or I'm sorry, 10 to the power of 7.4 mole per liter. So this is the expression of the pH. Of course, is better than hydrogen ion concentration because it is a very large number, a nanomole, of course. The relationship between pH and hydrogen, as you can see from this graph, is almost in the middle, linear. You can see from the graph. So 0.1 of each pH is changed with 1 nanomole of liter raised in hydrogen ion concentration. You see, measurement of pH of hydrogen ion concentration by electrode is simply we use what we call the hydrogen ion sensitive glass. This sensitive glass is being present the tip of the tube. You see, this sensitive glass has the cations. Most I will show you later on. It's made of lithium. It changes its cations with hydrogen. There is the potential which develops across the glass, which depends upon the difference, of course, of hydrogen ion across it. The sample of the blood or urine or CSF has a level of hydrogen, and so there is a potential developed. The pH of the inner tube is kept constant by a buffer solution. So the net result is the difference in potential, which will create the circuit whenever I complete the circuit with a reference electrode. The electrode present in this tube, the pH sensitive, is made of silver chloride in communication with a chloride solution, which is potassium chloride. So we complete the circuit with a reference, also silver chloride, separated from the sample by membrane so that it will not be contaminated. In the past, they used to use mercury chloride. Of course, it was found to be toxic. This is why they don't use it nowadays. Of course, the blood sample is being taken from the human being anaerobically and heparinized for analysis. The temperature must be kept constant, the human normal temperature, and if there is a sample coming from a hypothermic patient, we must make a correction. Calibration, of course, before use by 2 buffer solution. Each buffer contains fixed concentration of 2 phosphate buffers. This is by international agreement. The electrode system must be maintained for fear of development of holes or the deposit of proteins, so it must be cleaned every now and then. Of course, we must, as we said before, we can use instead of blood CSF or urine. Of course, there are specific electrodes for potassium, sodium, and calcium. So I can ask you a question: how do we estimate the level of potassium? You will tell me there is a special selective gas electrode to measure such level. The measurement of CO2 is also based on the pH electrode. We call it severing hose electrode. It is also based on the pH, where we have a pH sensitive glass. This sensitive glass has a silicon nylon mesh. This nylon mesh contains bicarbonate, and this system is being separated from the blood or CSF by a special membrane, which is attached by 2 pulleys, as you can see, to stretching the the membrane. So whenever CO2 goes through this system, which is specialized for CO2, it combines with water, creating carbonic acid, which is separated to bicarbonate and hydrogen. This hydrogen being measured by the meter directly in CO2 level. It's very sensitive, up to, as you can see, 130 Pascal. And we must take care, of course, to keep the temperature constant and take care of the holes and the deposit of proteins. It takes around 2 to 3 minutes to work. It's slow because in the time for the CO2 to enter the system and to create hydrogen at last. Of course, when you want to estimate the dry CO2, we must subtract from it the water vapor, as we can see from this figure. Suppose CO2 level is only 5%, so we multiply the 5% times the atmospheric pressure after subtracting the water vapor, which is 6.3. You know that always normal CO2 is around 5.3 kilopascal, but water is 6. So we ought to subtract this one, and then we get the final level of CO2 whenever it's 5%. New techniques, of course, for intravascular catheter, as we said before, as option to facilitate continuous measurement by the use of mass spectrometry. Also, you have a transcutaneous CO2 measurement like that of option. Now we go to the infrared analyzer. This analyzer gives continuous recording of the CO2 concentration. We call it the capnograph. The capnogram is the written level of the CO2, but the graph is the apparatus. It also can measure other gases that have 2 or more different atoms in the molecule, different, so carbon dioxide, nitrogen oxide, for instance, not oxygen. 2 dissimilar atoms can absorb infrared rays. In case of CO2, we ought to memorize this level of wavelengths, which is 28 micrometer for CO2. This is specific for CO2. How does this apparatus work? There is a emitting light going through a chamber, and we have a filter to control the wavelengths. This chamber, of course, contains the CO2 that I want to measure. You see, this chamber must be made of sodium chloride or sodium bromide, or it can be made by a material called sapphire. This material don't absorb infrared rays, but glass unfortunately absorbs infrared rays. This is why we use such materials. And then after absorption is going to be focused on a photo detector to give me the final result. We have sometimes, because this the source of light is changeable, and the detector may be not steady. So this is why we better to have what we call a reference cell, or we have a second beam instrument, so that the rays will come out from this chamber by a mirror, split it into two parts. One of the parts going to the, I'm sorry, before going to the chamber, one of the parts is going to the chamber, other one goes to a chamber where there is a CO2 free gas. So the final concentration will be subtracted from both of these chambers to go to the final reader. Whenever CO2 absorbs light, it increases the molecules in their activity, rotational and vibration energy. So whenever they are bombarding other molecules as nitrous oxide, they transfer some of their absorbed CO2 infrared rays to the nitrous oxide, giving enough more power to absorb more infrared. So it will make a phalanxes. This is called collision broadening, because the broadening, the range of CO2 absorption whenever they bombard CO2 will be changed. As we know that the wavelengths that is absorbed by CO2 is 28 micrometer, but it may be affected. This is the peak, but the brooding, it can increase the range of absorption. This is why whenever we have in the labs, we used to have an apparatus where we used to manually adjust it in case of using nitrous oxide. Nowadays, of course, this is automatically arranged. You see, this is what we call collision broadening. Capnographs, as we have two types of time. We have side stream and a mainstream. In the mainstream, the gas is being drawn typically at a speed of 150 milliliter per minute. You must memorize also this, because you have to put it in the example. And then after it's been absorbed, it goes to the analyzer far away from the patient. You see, of course, moisture trap is present there to remove the water vapor, and the exhaust port returns the gas back to the circuit whenever we are using a closed circuit, or transfers it to the scavenging system whenever we are using a semi-closed or open system. So the time taken for the sample to go to the analyzer, we call it the transit time. You see? So whenever I have a correct tubing and a proper flow, this is it makes a very minimal difference of accuracy. In the mainstream, we have a special connector A, the patient connecting system, the Y system, to the analyzer. In other words, it's present there, and this is why it's bulky, it's heavy, but it immediately absorbs CO2 and it creates the figure. Of course, it has a sapphire also window, so we are avoiding what we call the transient time. Of course, it's better to have a tracing of the capnogram, not just a figure of it. Otherwise, we will find difficulty to discover pulmonary embolism in case of sudden decrease in the amount of the CO2, or a hyper active situation where the CO2 is increased as malignant hyperpyrexia. The time taken for the capnogram to respond and give me a reading is called the race time. So we have two types of time. In the science stream, of course, the results can be about 400 milliseconds by use a small analyzer chamber, only in the figure of 1 milliliter. This makes the difference. Of course, slow flow will give a long rise time, and a high flow will make a much pressure drop, and this will be affecting the end result. Of course, whenever I want to measure trace amounts of suppose anesthetics in the atmosphere, I use long sample cell. This long samples, it is one of the methods to measure very minimal amount of gases in the theater, or we use angled mirrors to fold the beam. You see, you fold them, so you use angles to fold the beam, so that you can create a very long line of infrared to measure minimum amount of gases present in the atmosphere in the form of 3 parts per million. So gas chromatography also, and spectrometry and mass spectrometry and refractometer are called physical methods. But chemical methods use the decrease in the volume or pressure of a mixture of gas, the decrease in it whenever carbon dioxide is being taken. You see, so this is called a chemical method, not as the physical method. We have the colorimetric method, of course, as metacrystal purple, which turns the color to yellow in the presence of carbon dioxide. So, of course, we can use it to differentiate regarding accidental esophageal intubation. So this is a colorimetric method. The last point we'll talk about is the gastric mucosal pH. As you can see, it is a simple rail tube with ended by a silicone balloon. This silicone balloon is permeable to carbon dioxide, so we administrate it in the stomach. Of course, whenever there is a problem of a shock patient, of course, the splanchnic blood flow will be decreased, especially in the liver, in the stomach, so that we can whenever we adjust this balloon close to the mucous membrane, it will give me gastric mucosal cell situation. So this balloon is being the CO2 in it is equilibrated with what is present on the mucous membrane, and will be taken by the tubing system, especially if there is a pump for continuous measurement, and we can estimate, of course, the CO2 knowing the Henderson-Hasselbalch equation, where we notice the presence of the amount of bicarbon present, and of course, this solubility coefficient of carbon dioxide. Whenever we divide or take the logarithm of both of them, knowing the pKa, we can estimate the pH. These are figures that shows the electrode assembly. As you can see, we have the silver chloride, we have the tip glass electrode, which has most probably lithium. This lithium changes its cations with hydrogen, and this area has a buffer to keep the pH in it, and so that the potential is the difference between the pH CO2 present in this and in the sample, and then this circuit must be completed through a reference electrode, silver chloride, separated, of course, membrane to read the pH. This we can see the figure how that the cations are being changed to create the potential, and this is the figure showing the gas pH gas contains lithium to change with hydrogen, and this is the normal capnogram, and this is the figure where we have a normal, and then we have a chronic obstructive airway disease. You can see the steepy of the curve, and then this is a part where we have the congestive heart failure patient, and this is the sapphire chamber, and this is the mainstream capnogram, and this is some questions, and this is the difference between the side stream and the mainstream. You can see the bulky analyzer present at the connection of need by the patient, and we have find the tube that goes to the analyzer, and we have the fluid tap, which we said whenever it's in a small amount, it gives a more accurate, and we have an analyzer, and we have of course a pump. Either this taken sample is returned back to the closed circuit, or is being taken to the scavenging system. I hope that I succeed. I'm sorry for my mistakes. والسلام عليكم ورحمة الله وبركاته.